space travel and how maths can get us there. Over the past decade, there have been many technological advances in space travel, and with new information about maths surfacing daily, the prospect of travelling further away from Earth is becoming a reality. But how will we get there? Let's first take a look at where it all started. In 1687, Isaac Newton published a book called Philosophia Naturalis Principia Mathematica. It explained many important concepts, including shell theorem. Proven with calculus, shell theorem states that a symmetrical spherical body will gravitationally affect external objects as if all of its mass is concentrated at the centre, as shown by the diagram. In 1813, the Przewalski rocket equation was published. It describes the motion of rocket-like vehicles travelling at a constant speed. This simple yet effective equation is still used today in modern rocket science. In 1905, Albert Einstein theorized his special theory of relativity, more commonly known as E equals mc squared. This equation states that an object's energy is equal to its mass times the speed of light squared. From that day on, there were many more important events and discoveries, including in 1929, the first liquid-fueled rocket launch, in 1946, the first rocket to reach orbit, and on the very same day, the first photographs taken of Earth. In 1947, the first satellite was launched into orbit. In 1969, there was the first man on the moon. In 1970, there was the very first lunar rover on the moon, and in 2006, there was the launch of our fastest spacecraft yet, New Horizons. Our Centauri is the closest star system to our own solar system, being 41.32 trillion kilometers away from our Sun. It is made up of 3 stars, Alpha Centauri A, Alpha Centauri B, and Alpha Centauri C or Proxima Centauri. To put into perspective how far away 41.32 trillion kilometers really is, we use the time equals distance over speed equation to compare some everyday objects and organisms. A garden snail will get there in 100 billion years. A walking human will get there in 943 million years. Usain Bolt will get there in 105 million years. A cheetah will get there in 39 million years. A peregrine falcon will get there in 15 million years. A commercial aeroplane will get there in 5 million years. A bullet will get there in 1.6 million years. A rocket will get there in 162,543 years, and New Horizons will get there in 80,527 years. None of these objects and organisms, however fast they may be, will get us to Alpha Centauri at a solid amount of time, or what scientists are aiming for, which is between 10 and 60 years. But how fast will we need to go? Perhaps at the speed of light. The speed of light is approximately 300,000 kilometers per second, which is about 7.5 times around the Earth in a second. Though unfortunately, according to E equals mc squared, travelling at the speed of light is impossible because the mass of the rocket would be infinite and therefore the fuel needed would be infinite too. But what if we travelled at 90% of the speed of light, or approximately 270,000 kilometers a second? It would get us there quickly, and the mass and fuel required is not infinite. Now we know our aim to reach Alpha Centauri at 90% of the speed of light. How much fuel will we need to get there? An average modern-day rocket needs 2,066 million litres of kerosene to reach the moon. Though, travelling at 90% of the speed of light to Alpha Centauri, again 41.32 trillion kilometres away, we will need 34,282,539,800,000 litres of kerosene. Though, as technology advances, better fuel consumption will hopefully be invented, therefore making the total a lot less than that. Overall, combined with maths and advanced rocket technology such as laser light or solar sails, the goal of reaching Alpha Centauri is a lot closer than we might have originally thought. Overall, the technology necessary to send a rocket to Alpha Centauri within our lifetimes currently is not advanced enough, but with the combined use of shell theorem, Przewalski's rocket equation, E equals mc squared, the speed of light, and a bunch more amazing and complicated maths, we can calculate the dimensions, thrust, and speed of the rocket needed when escaping the Earth's gravity to reach our goal of 90% of the speed of light. We will travel through space and time, and maths can get us there.